Hello everyone. In this lecture we want to talk about digital versus analog signals. In the previous lectures we talked about Maxwell's equations, which are simply mathematical statements about the physical world which are true and they're experimentally verified. And the other idea was the layers of abstraction idea, which was basically a way to simplify difficult physics and mathematical concepts and not have to reinvent the wheel every time and just simply build upon previous ideas but not have to go through them again and again. Those are the two big ideas, and that's obviously a summary of them. If those didn't make sense, I recommend either reading up on them or going back to the videos or asking a certain question on the comments or email me about it. Okay, so now digital versus analog. Let's say we have some kind of device, something that we need to know the pressure that is exerted on it. So for example, it has some certain surface area up here and somebody's exerting a certain pressure on it, which is a force, and force divided by, just to refresh your mind, force divided by area is going to be pressure. So what we can do then is, to monitor that, we can think about, in a mathematical sense, we can think about, okay, let's make it depending on time. So as time goes on, somebody's going to be pushing up and down on it, and we can put pressure here and say, let's say it's just a curve that goes on like this. Okay, so what this is in general, what this represents now is a curve, and to be able to actually do anything with this, with electronics and electrical systems, we would need to convert this into an electrical quantity. Right now it's a physical quantity of pressure that is changing with time in a continuous manner. We're assuming that there's no discrete jumps, like nobody's like jumping up and down on it, where it would look something like this if that were the case, jumping up like that. We're not going to assume that. We're just going to assume that it's a continuous signal as such, as you can see. So what we got to do then is either have currents or voltages to represent this curve, a certain amount of current changing or a certain amount of voltage changing. Well, let's think, if we make it so that it's a current changing and representing this, well, that would be very costly, because you may not know, but you'll understand later on in this course that when you have a power source here, and let's see, plus minus V and resistance, when you have a current flowing here, and you can see if you wanted to represent this curve as a current, what would happen is you're going to go up and down here, and you're going to be losing power here because you're losing energy. The resistor is like friction, basically. You're dissipating energy away and you're never getting it back. So that would be kind of an expensive way to go about representing this. So what we do is instead represent these quantities, these continuous quantities, as voltages, because voltages can change depending on the device. They can change abruptly. Well, they can't do that on capacitors, but they can change abruptly on, for example, resistors, meaning change discretely, quickly. So what we can do is use voltages instead. And what we're going to do then, what's going to happen is when we change these into voltages, that's going to be an analog signal. Right now it's a physical signal. And to be able to do any manipulation or computation on this, or data keeping, data recording, we're going to need to turn this into an electrical quantity. And we determine that we don't want to use I because it's going to be costly and we're going to be losing energy, never getting it back. And as analog of what I'm talking about is this. So for example, if you want to understand why we can't use current, if you think about some like ground here, and you wanted to like draw something down here. For example, I'm just kind of coming up with this now. So if you want to put a box on the ground and kind of like use it to like draw something, and what you're doing is like pushing it back and forth and so on and so forth, just pushing it back and forth here. Well, what's going to happen is that it's going to, the friction between here and ground is going to make it so that you're losing energy to heat and heat, temperature, and vibrations, basically, and you're never getting the energy back. Whereas if you use, for example, a oscillating a perfectly, let's assume it's a perfectly lossless spring, meaning the spring does not lose any energy, which is not, in the real world that's not the case, but let's assume that is the case for now. You have some mass spring system, and you're using this, for example, to have some pen or pencil attached to it and have it near a wall, and have the position be recorded by the movement of this, and it's going to look something like this, for example, right? It's going to look something like that. Well, here we're dealing with potential energies, the potential energy of gravity, which can easily be replenished, and I'm kind of trying to draw an analog between the two and show you why it'll be more costly in terms of energy to use this system to draw something on the ground, as opposed to, for example, use potential energy, which is in a conservative field, in a gravitational, which is a conservative vector field, using that potential energy to represent the same kind of behaviors. So that's kind of an attempt to try to draw an analog here. The voltage would be there, the potential energy, and the current would be that the kinetic energy here, and being lost through that friction. So that's that idea there. So then what's going to happen here is you're turning that pressure, going back to what we started off with, you're turning that pressure into some electrical quantity, so we determine it can't be the current because it's too costly. So using that voltage, then what's going to happen is you're turning into an electrical signal to kind of process that signal. You're going to turn that thing into a voltage signal, and then you can do some kind of manipulation, some kind of math to it, and determine some stuff about it. Like, for example, the amount of force, like have this guy divide that by the, let's see, implement some kind of mathematical function to determine the parameters that you need and make the necessary calculations you need. So this would, for example, be an analog signal then, because it's a continuous signal, as you can see, and there are no discrete jumps. So let's think about some of the downsides of such an analog signal. Well, suppose you have some device, some electrical device that is doing this, is turning a physical, let's draw it like this. You have, let's see here how to draw this thing. You have that box that we talked about. You're exerting a force on it, which in turn, if that's the area, the pressure is force divided by area. So what this guy is doing, this electrical device, is going to be measuring that somehow and turning that into an electrical quantity, voltage, and it's going to be like outputting that. So let's think about this though. Let's draw the same graph. This is theoretically what the pressure would look like. And what's going to happen now is that this device over here is going to try and convert, through whatever mechanism that it has, it's going to try and convert this into a voltage signal. And in doing so, we got to think though, remember how he said we're going to assume this is 0? We said let's assume that there are no induced electromotive forces or any interference or anything like that. Well, if you think about it, in the real world there is such a thing of electromagnetic interference, and what's going to happen is that as this guy is this device is outputting a signal to some computer for manipulation, what's going to happen is this original signal is going to have some kind of jitter in it as such, due to just natural electromagnetic interference from other signals, other devices, supernovae, the sun, any kind of electromagnetic signal that is called noise. We call that just noise. So let me draw that here as noise. Draw it better. We call it N here. Just call that noise going into the system here. And that's what it's doing here. Making a jittery signal over here. So that's one downside of analog signals, is very bad interference. So let's think though, if you go into what's called a digital signal now, the difference is, what you're going to have is discrete pulses here now, which can be represented as zeros and ones. So a low state would be 0, a high state would be 1. So let's talk about the advantage now. Let's call this voltage again. Let's think about the advantage here. What are the advantages? Well, what's going to happen here is, what we can do is define a certain margin for this kind of system, for that same kind of device, instead of using an analog one as we showed up here, that is very has very bad weakness of being having jittery signals when electromagnetic interference is introduced to the system as input. What we can do is now use the digital system and define a certain threshold. For example, let's say that's 5 volts, and let's say from anywhere from let's see, 2.3 volts to anywhere from 0 to 2.5 volts. 0 volts to 2.5 volts would be considered a 0 signal, 0 input. Anywhere from 2.5 to 5 would be a 1. So what's going to happen now is, when you do get a jitter here, when noise is added to the system, you'll get a certain jitter. Let's draw the signal here now. With noise added to it. Draw it over here. Add noise into here. What's going to happen now is you're going to get something kind of similar to this. You're going to have the 5 volts maximum voltage up here, the 2.5 volts here, and the 0 volts here. And your function is going to look something like this. Some jitter again. Just electromagnetic interference. And you can see that even though I have had electromagnetic interference, I still have the defined threshold, and this is still read as a 1, as it was a 1 here and a 0 here. Anything below this line is a 0, anything above it is registered as a 1. So what I've kind of done here is, I've introduced a kind of immunity to this digital system to be to not have to worry about electromagnetic radiation as much. Now, do remember though, if the electromagnetic radiation is very strong, very considerable, we can get, for example, a very bad jitter to where it might not register as a 1 anymore. It'll be an unreliable system, and basically we can't rely on it. If you get it a 0, sometimes it could give us a 1, sometimes it could give us a 0, so it can't be reliable. And we'll get into those in a digital system course, so we're not going to worry about that here, but this is just an idea of analog and digital systems, and I hope that you've kind of gotten the idea of what the difference between them is. And I'll just mention this, that for the longest time before the digital revolution, we used the devices that we talked about, for example op amps, to do calculations and things of that nature. For example, 5 volts and negative 5 volts. I'm going to get to this soon. Actually, not soon, maybe in chapter 5. So, the idea is that this is what we use for analog signals, and that interference was a very undesired thing that we had, but and also the math was kind of complicated. We used differential equations and things of that nature. But then when we got to digital signals, it was pretty much adding, subtracting, doing math, simple math with binary numbers. So like this kind of numbers, which all represent some value at a base 2. So you can see that we get the conclusion is that using digital systems, you would get kind of a defined immunity to noise based on our voltage threshold, and our math becomes kind of simpler. Whereas with the analog signals, we have a little bit more freedom to make any signal we want, any continuous curve we want, but then it's kind of more, it's less immune to electromagnetic radiation. It's more prone to be interfered, or let's put it, shall we say, put it this way, electromagnetic interference noise would have a greater impact in making jitters in the signal and making it an unreliable signal than the digital signal. And so yeah, as we said, the math would kind of be more complicated in doing that. Okay, hopefully you understood what we've been talking about, and if you have any questions, again, please feel free to comment and message me and email me so I can clarify some concepts here. I'll see you in the next video, and thank you for watching.